Yeah, welcome to Numerical Methods. And we are still now in our section on computer arithmetic. So now let's discuss a nice example, where you see that the problem is 1 plus epsilon equals epsilon, leads to real world problems, or problems in numerical methods. So the rounding leads to this effect. Floating point number 1 plus epsilon is equal to floating point number 1 for epsilon small enough, less or equal to the machine position in our case here. And this leads to unexpected results. And the example I would like to discuss is the solution of this quadratic equation. X squared plus px plus q equals 0, where p is quite large, q is not so large. Okay, well, the difference is big. I believe this here is 10 million. Let's check. This is a 10 million. But maybe the computer should cope with this. And you maybe recall that the solution is given here by this formula. So if I look at the smallest solution, then it is only the formula that has a minus here. There is another solution with a plus, but if I only look at the smallest solution, it is the one with the minus. So it's minus p half minus the square root of p half squared, so p squared divided by 4 minus q. Actually, there is an alternative representation, not so popular, so which you immediately get. If you multiply this guy with the other solution, so the minus p divided by 2 plus square root of p squared divided by 4 minus q. So if you then just make this modification, I multiply this with this and I divide by this, so I have not changed the formula, not changed the result. It's still the same smallest solution. Okay, then you see that on top you get a minus p half squared minus the square root squared. Okay, which will give you just a q on top, and you now divide by the other solution. So q divided by the other solution is this smallest solution. Now this is just an alternative way of representing this solution, and I would like to calculate this. Maybe we have enough time to do this live. So let's create here a new class, call it quadratic equation experiment. I would like to have a main method. Now I have to type it myself. This ugly line. Define our parameters. So on the slide, it was let's see, minus 10 million. 10, 1, 2, 3, 1, 2, 3. For the P, and for the Q, it was 1.0. So let's calculate the solution. So this is the smallest root of quadratic equation, taking our formula version 1. So I still have to implement this, but once I have implemented it, let's print the solution. Okay, the solution is our x1. Okay. And maybe let's also print the check. Yeah? The check is I plug this solution into the equation. So let's have x squared plus px plus q with x equals x1. And let's also print this. So I have here x1 times x1 plus p times x1 plus q. So I can check the result. So let's implement here my formula. So my formula for the p and q. So this is minus p divided by 2 minus square root p times p divided by 4 minus q. So let's keep fingers crossed that this code is correct. Run it. Okay, and I get the solution x1. Now, it's a fairly small number, 10 to the minus 8. But if you make your check, you see, actually, it's not a solution. And the error is quite huge, huh? You missed the 0 by quite a lot here. Did I do something wrong? Is the formula wrong? Minus p half minus, everything looks correct, right? Let's try the other way. Yeah? So I now call this double x2, yeah, but it's still the same solution. Yeah, it's not the other solution. It's still the smallest root of the quadratic variation, quadratic equation, but in a different, calculated with a different version, with a different formula. Maybe fix typos here. This is version. So I have to implement this method here. So this is now my other formula. So how is this formula looking? So it was take Q and divide by actually the guy with the plus here. So this is my alternative way of calculating the solution. So let's print this x2 and also do the check now where x is replaced with x2. And let's keep fingers crossed and see what we get. Yeah, you see, it's a very similar solution. It's a 10 to the minus 7. Yeah, this here is a 9.9 times 10 to the minus 8. So it's also almost 10 to the minus 7. Yeah, but this guy is the solution. Yeah, so this guy is solving the equation. The other guy is not solving the equation. Okay, so you see that actually this numerical method here can go wrong. Okay, and why is this happening? What is going on? Yeah, if you look at our exercise here, what we are doing, the solution is the difference of a large number and a large number. Yeah. And these two large numbers, I mean, think of the case where Q is 0. If Q is 0, then actually this here, square root of this here is the same, yeah. Then the two are on a similar scale, yeah. So the P is minus, so actually you go quite to a 0, yeah. So the solution is the 0. So actually it's just this Q that is really deciding how far I am away from 0. But this, or how far the solution is away from 0. But this is expressed as the difference of a large number and a large number. And there I have a loss of significance. Actually, I would like to have accuracy that I need for small numbers, but I moved to a scale that was associated with large numbers where I do not have this accuracy. Here, actually, it is the sum of a large number and a large number. So this is the other solution. This is large. Yeah? So this here is a plus, yeah, but here is a minus, and my p was a minus. So this is also a positive number. Yeah? So these two are large and positive. And the problem is that we have a minus, yeah, difference of two large positive numbers. Yeah, here the nice case is we have a plus the sum of two positive large numbers. So this operation is perfectly fine. And then I make a division, yeah, divide a small number by a large number. Okay, it gets a little bit smaller, but it can represent small numbers. This is the reason why this thing here is so much better. Yeah. Okay, and you see it's related to the 1 plus epsilon problem. I mentioned that we have computer assignments prepared for you, and there's one computer assignment related to this, so maybe I show you this here. When you accept this assignment in GitHub Classroom, he will create a fork of my template repository. So this repository is created for you, and you have your own Git repository with the code where you can work on. Yeah? So you can now check out this repository and then work on this assignment, on this problem. In all these assignments, there's a README file, yeah, which is also printed here, which describes what you should do. So here you should implement a generic, say, class that solves these quadratic equations in a way such that he is always providing you a good solution. Yeah, so he should maybe choose which of the two ways he takes, yeah, to calculate the solution. So you should calculate it in a numerical stable way. So there is a little bit prepared for you. Yeah, so I created an interface. So if you go to the source file, yeah, you see there is already a test that tests your implementation, and there is a solution prepared, yeah, but in your solution you see there is here an exception, unsupported operation, method not implemented. So your code should go here. Yeah. So often these are fill-in exercises where everything is almost done, yeah, but the crucial things are missing, and you should fill in the solution. If you then run your solution, he will perform automatic tests, unit tests. He's performing unit tests. This is also done if you commit your solution to the repository. So whenever you commit a change to your code, to your repository, he is running these tests. And you see that here the initial commit had a failure. Yeah, you can have a look to this failure. All checks have failed. These checks can be seen here. And you will get points if the check is succeeding. So currently I have 0 points. If you click on this, you can also see what went wrong. Yeah? So he tells you, okay, he made a test, yeah, and the method is not implemented, so the test failed. Yeah? So you see he is testing with different coefficients here, yeah, testing if your solution works. You can find a video that describes a little bit how you work with these assignments in our list of videos, and I hope you have fun working with these problems. Yeah. So sometimes you get points. Yeah, it's not binary. If you make a partial solution, sometimes you get all partial points. But here for this, actually, I believe it's just you get 4 points or you get nothing. Yeah, it's not such an difficult exercises. Yeah, so that was a small remark on these assignments. Yeah, can you explain why the two different ways of writing the solution differ in their computer arithmetic? Yeah, we did this. It's because cancellation, difference of two large positive numbers versus the sum of the two large positive numbers. And this is the corresponding code session. So you find the experiment here. That was loss of significance.